Okay, so good morning, everyone. Okay, so this will be our final lecture for this semester. All right. So in this lecture, we will cover two new sort of subtopics on address decoding and DMA. And after that, we will go through some details regarding the mini project as well as the final exam. Okay, so let me start. Okay, so let's get started. Everybody can see my screen. Yes. Okay. Thank you. All right. So this is the address decoding topic. Okay. That I said I will add in. All right. So this is new. Probably never been taught before in any other module. I think here. But this is an important sort of concept you must understand because as embedded engineers, we must learn how to design the hardware and also do the software, correct? I think the trend in recent years is that a lot of hardware is ready-made, correct? Just plug and play. So that sort of makes your life easier, correct, to prototype and get things moving. But then that learning has been sort of missing in the last few batches of students because they don't get to build the hardware. They don't get to realize how challenging it is, all right, to build your own hardware system and then do the software on it. All right, so that part is what I'm trying to bring back. All right, so this is the first step. All right, so I will release one more set of lectures, all right, on virtual memory. All right, so that is also another thing that is good to know, that is also related in some sense to OS and computing systems in general. Okay, I will release those slides, but those are not examinable. Okay, that is for your own reading, okay, for you to look at when you're free. Okay, but this until this topic is what is examinable. Okay, address decoding and DMA. Okay, so let me get started here. All right, so what is the whole idea of address decoders in the system? All right, you want to be able to have many subsystems. All right, so if you think about it, all right, a microcontroller. Okay, so as you know, okay, so as you know, a microcontroller is actually a complete package, correct? But rightfully, you have a microprocessor, all right, and then you have, of course, your memory, okay, and then you have your input output ports, okay, and then you have your other peripherals, subsystems, and so on, okay, and then of course you also have your main things such as your clock, all right, then you have your power and so on, and all of them is sort of packaged together, and then you have a microcontroller. All right, so that is your micro and macro perspective. Okay, so if you want to design your own system from a processor level, you need to be able to understand how to connect these various devices. All right, and this also applies to microcontrollers because some microcontrollers also allow you some level of flexibility in terms of addressing to add on more peripheral subsystems. All right, so we want to have the idea of how do I connect different subsystems. All right, so from a microcontroller, okay, when I want to connect to more memory chips, for example, okay, so maybe the current memory is not enough and I need to have more memory. Okay, how do I connect this memory to my system? Or if I don't have enough IO ports, I need some more IO. How do I connect it to my system? Correct, in terms of assigning it to specific memory location. All right, generally when you say address decoding, it is targeting at the processor level and you're trying to build up everything to specific addresses. Okay, and then at the microcontroller level, you are trying to see how you can extend it to add more peripherals. Okay, so what we need to do is we need to understand what is the addressable memory space. Okay, what is the addressable memory space means? What is the address bus width of your system? Okay, so this one we need to look at the address bus width of your processor you are dealing with. Okay, and at the same time, you need to look at, okay, what are all the systems or subsystems you need to connect. Okay, so definitely you need memory, then you also need your peripherals. All right, and what is important is for a given valid address, that particular component must be accessed. Okay, so if you look back at your kill environment, correct, when you were doing the port register addressing and serial port, all these things, we were writing to registers, correct? So when you're writing to registers, if you look at the address mapping, they were mapped to specific addresses, correct, which you can see in the data sheet. All right, so how did this mapping come about? How do we say that this peripheral is mapped to a particular address? All right, so that is what we are going to look at. Okay, now address capacity of memory basically is defined by the width of the address bus, and it tells us how many address locations or how many different memory locations we can actually access using this address bus. All right, and address capacity is double for every address line that is added. Okay, so from 7 bit it becomes 8 bits, it becomes double. Correct, but every time you double the number of possible address locations you have. Okay, so for example, if I have 2 bits, okay, A1 and A0, if I have a 2-bit address bus, you only have four possible values. Correct, the moment I add one more, what happens? Then it becomes 8 and so on. So every time I add one more address line, the total number of address spaces I can access becomes double. Okay, so the whole idea of designing address decoders or address decoding is to ensure that you generate the correct chip select signal for the address bus. Okay, so what is this chip select signal? This chip select signal is basically a pin on a peripheral that activates it. All right, when you are connecting hardware to your processor or your controller, okay, you may not want or do not want that particular chip to be switched on or active all the time, correct? Then it may be a waste of your power. Okay, so you want to activate it when you are going to use it. So the idea of address decoding is when I want to activate, when I want to communicate with a particular peripheral, then I activate it by making sure the chip select is in the correct level. And once that is done, the device is ready for communication. The way we do this is, the strategy behind it is, we look at the address bus, all right, and we break it up into two parts. All right, the lower bits will go towards the memory system, all right, or the register of whichever device you're mapping to, and the upper bits will go to the decoding. Okay, the upper bits will go to the decoding. All right, so the way we look at it is, these lower bits that go towards the memory or peripheral are the ones that will keep changing, whereas the one that go to the decoder are the ones that will be remain constant throughout the entire access. Okay, so later when you look at the example, you will see how this sort of works out. Okay, so let's look at this example. So I have 10 address lines. So if I have 10 address lines, basically it is basically saying it is from 9 down to 0, correct? That means it is to the power of 10, and that is 1 kilobyte of memory. And I want to populate its entire memory space, all right, with 128 by 8 memory chips. Okay, so 128 by 8. So 128 bytes is 2 to the power of 7. Okay, that means it is 6 down to 0. All right, so if I look at it, what I have is I have 10 address lines. Okay, total of 10 address line, 9, 8, 7, 6, 4, 3, 2, 1, 0. And each memory chip requires 7 address lines, correct? To make sure that within that 128 byte space, I can access all the memory locations within it. All right, so that is for the lower 7 bits. All right, and then the remaining 3 bits is what I will use to do the decoding. All right, so these 3 bits will be used to decode and select the appropriate memory chip, and then this will be used to address the memory. That means within each memory, I will be able to address all the locations inside it. Okay, so if you look at the next slide, okay, so what am I doing here? Okay, so the first thing is you can see that in my processor, I have a 10-bit address bus. All right, I have a 10-bit address bus that comes out, and out of the 10 bits, this is the lower 7 bits. The lower 7 bits automatically get mapped to the address bus of all the memory. So this, all this is the address bus of each memory chip. Okay, and you can see that it goes the same 7 bits to all the memory chips. So when a 7-bit address comes out, all right, okay, or when a 10-bit address comes out, the lower 7 bits automatically are sent to all the memory chips at the same time. All right, so that's the first thing. Now, definitely I cannot activate all the memory chips at the same time, then all of them will try to communicate on the single bus. All right, and then you will get garbage. All right, you won't be able to decode anything. All right, so at any point of time, I only should activate one particular memory device. So to activate only one particular memory device, I will use the upper 3 bits. Okay, so when I use the upper 3 bits, what happens? Okay, so if I look at the mapping here, so A9, A8, A7, and A6 down to A0. So A6 down to A0 is always mapped to all the memory chips. So when A9, A8, A7 are mapped to this 3 to 8 decoder. Okay, so what is the 3 to 8 decoder? You all should know what is the 3 to 8 decoder, correct? What does the 3 to 8 decoder do? Okay, correct. Okay, so it's basically taking the 3-bit input and activating one of the output lines, correct? It is taking a 3-bit input and activating one of the output lines. So if my input is 0, 0, 0, all right, then the line 0 will get activated. Okay, when the line 0 gets activated, then the mem0 will be a chip select will be active. So this device is the only device that will be talking to the CPU. Okay, so as long as the upper 3 bits is 000, whichever address I map to here. So from address 0 all the way to 1 to 8. Okay, so this 1 to 7. Okay, so this first 1 to 8 bits, 1 to 8 bytes will automatically be mapped to the location where the upper 3 bits are 0. All right, when the upper 3 bits are 0, 0, 1, then I will start to activate mem1. All right, and then this will be from 1 to 8 onwards, all the way to 255 and so on. Okay, so you can see that by doing this approach, what you are able to do is you are able to say that at any point of time, I activate a particular memory chip on my memory map. Okay, so this memory map is basically like similar to what you have for your KL25Z. All right, only thing in your KL25Z, you have different memory controllers, peripherals, everything inside that. Okay, later we will have a look at that. Okay. But this is the same thing or the same approach that chip designers take when they want to manufacture and design a new microcontroller. They will look at what are all the memory systems I want to put in, what are all the peripherals I need to put in, which are the address locations I need to map them to, and then based on that, I design a decoding circuitry so that when this address is put on the address bus, this particular hardware gets activated. Okay, so all this is basically the back-end work you need to do if you want to design your own sort of system from the processor level up. Okay, so basically what I showed you just now is basically what you call the full address decoding. That means I use all the address lines to specify memory location. Okay, you can also use another approach, which is a partial address decoding, where your circuitry can become simpler. All right, but then you have an aliasing effect. All right, where you have multiple address locations selected for the same address on the address bus. Okay, so let's look at that. So in full address decoding, okay, so let's look at it as the same example as just now. But now instead of saying I want 1024, it means instead of saying I want 1 kilobytes of memory, I want only 512 bytes of memory. Okay, and I'm still using the same 128 byte memory chip. All right, that means I only need times 4. So, all right, 128 times 4, I'll get 512. Okay, so I only need 4 memory chips. Okay, so if I'm only going to use 4 memory chips, okay, I can still do the same design, but instead of using a full decoder, I can just do some simple logic like this. All right, where I use some AND gates, NOT gates, and so on, and come up with a circuitry. Okay, that relates the A9, A8, A7 to the chip select of the 4 memory chips over here. All right. Now, what you observe here is you see that in this case, each address will activate only a single memory region because I use all the address bits. Okay. But let's say you want to simplify your design and then you observe that, hey, A9 is always 0. Right? In my case, A9 is always 0. So why don't I omit A9 in my design and simplify the circuit? All right, so if I decide to do that, okay, I omit A9, then I only use A8 and A7 for decoding. All right, and it will still work. All right, your circuit is definitely now simpler, and I only use 2 bits. All right, and the decoding still works. All right, but now you have this aliasing effect because since A9 is not factored in, the same chip select will activate regardless of whether A9 equals to 1 or 0. All right, so when A9 equals to 0, I will activate this region. But when A9 equals to 1, I will activate this region. Okay, so since A9 is not factored, it will sort of activate 2 separate regions for the same address that you have on the bus. Okay, so of course, this is possible, okay, if you do not have any further expansion plans, correct? But in most cases, manufacturers will not use this approach because they always have a long-term plan, correct? They will create a controller and then they will have a longer term plan. Okay, later we will, after 6 months, we will release an upgraded version with more memory or more peripherals and so on. Okay, so if they simplify the address decoding circuitry in the beginning, then later on there's a lot of rework to be done. Okay, so if I implement a full address decoding, then it's a lot easier to go ahead and do it this way. Okay, so how do you implement address decoder? So what we saw just now is basically the discrete logic method and using data decoders. All right, so this is the way we can do it. You can use simple gates and put them together and design an address decoding circuit. You can use higher level chips like your decoders, multiplexers, and so on to design them. Or you can also sort of program them, okay, using FPGA methods or programmable ROM and so on. Okay, so it's all up to the complexity of the circuit that you're building and how you want your address decoder to look like. Okay, so let's look at this example. Okay, so this is a slightly more complex example. Okay, so if you look at this, what do you observe? Okay, so you observe that firstly, how big is my address bus? Just give me a minute. Okay, so we have a total of 16 bits, correct? Okay, 16 bits address bus. So in the 16 bits address bus, you see that you have a decoder over here, and you have another decoder over here. Okay, so you have two separate decoders over here, and you need to observe how the address lines are connected. All right, then only you can relate the circuit to the memory map that you see over here. Okay, so let's look at it step by step. Okay, so the first thing you'll observe is A15 is tied to this decoder here, and again, like I mentioned just now, many of these hardware blocks or devices will have some chip select, and in some cases we also call it an enable pin. Okay, chip select or chip enable or enable. All right, in this decoder here, you have three different enable pins. Okay, the E bar means you have to have an active low to activate it. That means a 0 to activate it. The E by itself means a logic high, so a 1 activates it. And this center one E bar is also active low. Okay, that means in order for this decoder to be active, all the enable pins must be in the correct state. Okay, so the E bar on top and the E below is already in the correct state, and the E bar in the middle has to be in the correct state. That means A15 has to be 0. Okay, so that's the first thing you must observe. A15 has to be 0. Okay, in the entire sort of approach here. Now let's look at the A14, A13, and A12. So these three are connected to the decoder chip over here. Okay, these three are connected to the decoder chip over here. So like what we saw just now, when it is 0, 0, 0, for example, I will activate the first chip. All right, when it is 0, 0, 1, I will activate the first line or second line. All right, first line or second line. So 0, 0, 0 activate the first line, 0, 0, 1 will activate the second line, and so on. Now, when I'm activating the first line, okay, so let's say 0, 0, 0 activating the first line, it represents that A11, okay, to A0 will all be used, okay, towards the actual device. All right, so A11 to A0 is total is 12 bits. Correct, so this is 2 to the power of 12, which is 4K. Okay, so that means each device that will be selected, okay, from this Y0 will actually have a 4K space. Okay, so that is why each of this ROM over here is actually a 4K ROM. Okay, if I were to have used a 8K ROM, then of course I would have shifted it. That means I would have used A0 to A12 to the ROM, and then I'll use the other bits for the decoding. Okay, so what bits go for decoding and what bits go to the address bus of your actual hardware depends on the memory space that you need to address. Okay, so since I have 4 ROM chips over here, and each of these ROM chips are 4K blocks, I need to make sure that the lower 12 bits are directly connected to the ROM chip, all right? And then the upper 3 bits are now used to decode. Okay, so Y0, Y1, Y2, Y3, all are the same. All of them have access to the 4K blocks. Okay, so this first block will be from when all of it are 0 until when it is 0, 0, 0, and 1, 1, 1. Okay, so that is the first 12K block. Okay, then the next 12K block is when it's 0, 0, 1. Okay, it will start off with all zeros and then until it all becomes 1. So that's the next 4K block and so on. Okay, so you have 4 blocks like that for the 4 ROM chips. Okay, now you have another Y4 and Y5, and Y4 will be selected when? Okay, Y4 will be selected when it is 1, 0, 0 and 1, 0, 1. Okay, now you can see that this is a OR gate, okay, with active low input and active low output, which means that when it is 1, 0, 0, it also gets activated. When it's 1, 0, 1, it also gets activated. Okay, because they are connected to a OR gate here, where both are active low inputs and I have active low output. So each of this gives me a 4K access. So together I have a 8K access. Okay, that means the entire memory space, all right, from hex 4000 up to hex 6000, that means the space is actually going to be accessing the 8K chip. Okay, so this is how you can actually use this single decoder. Okay, and even though your mapping here gives you access to 4K blocks, all right, because you're using A11 down to A0, you can combine them together and create an 8K access or 16K access. All right, because you can combine the outputs of the decoder together and activate a single chip select at the output side. Okay, so that is the 8K block. Now let's look at the other one, which is the hex 6000 space. Now for the hex 6000 space, basically what you have is, okay, maybe I write it over here. Okay, so for hex 6000, so A14, A13, and A12 all will be 0, 1, 1, correct? Then the Y6 gets activated. All right, when Y6 get activated, okay, what you observe is that it connects to the enable of this particular decoder over here. All right, and in order for this decoder to work, or any device to work, all the enables must be in active state. So A11 over here, you can see is also tied to E bar. That means A11 must also be 0. All right, A10, A9, A8 are tied to an active low input AND gate. All right, which means that all these 3 must also be 0. So A10, A9, and A8 must also be 0, 0, 0. All right, and then you have A7, A6, A5, which are mapped to the selector input C, B, and A. Okay, and then you have the remaining A4 down to A0, which is the space allocated for the device you are selecting. Okay, so this A4 to A0 is 5 bits. So 2 to the power of 5 is 32. Okay, which is 0x20. Okay, so that is why you see over here that each of this space here is increasing by 0x20, 32 memory locations. Okay, now basically what is happening here is when the upper bits are all following this, that means A14 is 0, A13, A12 is 1, 1, and A11 to A8 is 0. Then A7, A6, A5 will connect to the inputs of this second decoder to activate one of these outputs here. Okay, so when A7, A6, A5 is all 0, 0, 0, what will happen? The first Y0 gets activated. Okay, and this only when this gets activated, we must understand that the upper bits A15 down to A8, so A15 is still 0. Okay, A15 down to A8 is already fixed. Correct. So when it's all fixed, the only thing you need to look at is the last byte. Okay, the last byte over here, A0 to A7. So when A7 to A5 is 0, 0, 0, then I look at the last 5 bits over here to say that these 5 bits will map to the peripheral that is selected by 0, 0, 0. So that is why you have the first peripheral device that will be from 6000 all the way to 6020. Okay, so basically if you look at it, it is from 00 until okay, so maybe it's from 00 until 601F. So this is the first 32-bit location. Alright, because this is the lower 5 bits. Lower 5, you just look at the lower 5 bits only. Okay, then the next one will be 0x6020 to 0x603F and so on. Okay, so that will be the second peripheral space. So this is also again 32 memory locations. Okay, so your address decoding is basically trying to make sure that you connect the correct address lines to the various inputs, okay, of your decoding devices to make sure that each of your memory or your peripheral devices have a unique address. So when I write to this address 6020, for example, I know that I'm writing to peripheral 2. Correct? It's the same idea. Correct? When you write to a particular register, port A register PCR, okay, it is mapped to a particular address. Correct? How do you know it goes to that particular address? Because they have already designed the address decoding circuitry to make sure that when I write to this address location, it is actually going to that particular register, which is for the GPIO peripheral. Okay, so that is the idea of address decoding. Okay, so of course, it takes some time to go through and understand this. Okay, so you need to go through step by step again to make sure you understand what is happening here. Okay, how are the address lines being translated to the address space you have over here. Okay, so that is the way in which you can do it. Okay, so of course, this is the final solution, and definitely this is not trivial, correct? It is not trivial. It requires a fair amount of thinking and effort to decide and design this, correct? So of course, the easier way is you can put everything into some FPGA chip or a programmable ROM in a lookup table, correct? So in a lookup table, basically it's like a software-based approach, correct? You just say that, okay, what is the input address? Okay, so I have an input and I have output. All right, so input is basically all the address range. Okay, and the output is the chip select that I want to activate. So instead of designing the hardware, I can code it in some FPGA or programmable ROM or anything like that to have some tables to just map directly. All right. So for more complex devices like microcontrollers and so on with a lot of subsystems and peripherals, this is probably the approach to take. Correct, because you have a lot of subsystems, you have a lot of registers. Okay, so to design a circuitry from ground up is going to take a lot of effort. Whereas you put everything in a lookup table in software, it's a lot easier. All right, and let the FPGA handle all this translation of address to the chip select or register access pins. All right, so if you want to put it in software, it will just be a simple if else or switch case kind of a statement that you can write to say that when this address is on the address bus, I activate this particular chip select pin. All right, so that is the easier way to do it. Okay, so that basically is about the whole address decoding concept. Okay, so later when we go through the tutorial question, you have another sort of chance to look at it and see how it works. Okay, so the last part is on DMA. The DMA is also a very important peripheral. The good part is the KL25Z does have DMA. All right, you can try it out on your own. Okay, when you're free. All right. I initially wanted to put that in the first half, but then I realized that we didn't have enough time. Okay, if not, the RTOS part would get pushed further down. Okay, so that's why I didn't go through, but you are free to explore. Okay, so it is good that the board has it. So even though what we learn here, you can go and try it out. Okay, when you're free. Okay, so what is the purpose of a DMA block in a controller is it allows you to move data between a peripheral and a CPU memory without direct intervention of the CPU. Okay, so instead of making use of a CPU, all right, to move data. Okay, so normally when we say we have copy paste data, all right, move from one location to another location, that involves execution of code. I need to fetch the instruction that says copy data. Then I need to execute the instruction. Then I need to have another instruction to say paste the data somewhere else. Correct. So even though I'm moving data between memory location, it involves a lot of the CPU because I'm executing instructions to perform this memory move. Okay. With a DMA, you can sort of make this thing happen in the background without the CPU getting involved. Okay. So it's the fastest way of doing it, and it allows the CPU to do other more useful work. All right. So that is the main idea of having a DMA in your system. So basically what you have is, okay, so normally you have your CPU, you have your memory, you have your peripheral, okay, CPU, memory, and peripheral. Now you have your DMA controller, and your DMA controller also has access to the address bus and data bus. Okay, so normally during operation, you say that bus switch 1 is closed, okay, where your CPU is accessing the memory through the address bus and data bus. So CPU controls the bus. All right, but the moment your peripheral, let's say, wants to do a DMA transfer, okay, so for example, now my hard disk drive, okay, there's a requirement to move 1 GB of data over from one location to another location. Okay, so what you can do is you can initiate a transfer request. So it's again part of the DMA system in your controller, and what it will do is it will then request a DMA cycle from the CPU. Okay, so the DMA controller will request a DMA, will send a DMA request to the CPU because CPU could be busy doing other things, correct? So you send a request, say that now there's a request to do DMA transfer. All right, then what will happen is the CPU will return with the DMA grant to say that you can now take over the bus to do the DMA transfer. Okay, so once the DMA grant is given to the DMA controller, it knows it can go ahead with the DMA transfer. So what will happen is bus switch 1 is open and 2 and 3 are closed. So this is open, okay, and 2 and 3 are now closed. So now the DMA is taking over the address bus and data bus. Okay, so it can now move data around freely without the CPU. All right, so the peripheral is now able to communicate directly with the memory using the DMA. Okay, and once it is done, okay, it can, so basically you transfer the grant, and once it is done, it can send signal back to the CPU to enable it back, all right, to the enable CPU. Okay, so that will allow the CPU to get access back to the bus while disabling the DMA block from the bus. All right, so that is basically how the DMA controller can actually help you with memory move, okay, within the system without getting the CPU involved. Okay, so it is not necessary for the DMA to initiate it. The processor can also do it. Correct. So in your software itself, you can write the code, all right, to say that now I want to do a DMA transfer, correct? I have a huge chunk of memory to move. I don't want the CPU to do it. I want to do it very quickly so I can get the DMA to do it. Okay, so the CPU itself, okay, can send uh, uh, DMA request, okay, and get the DMA acknowledgement and then tell the DMA what to do. All right, so it can be done both ways. The peripheral can do it, or the CPU can also do it. Okay, so there are two modes of operation, okay, for a DMA. One is what we call the burst mode. The other is called the cycle stealing mode. Okay, so in burst mode, basically what you have is the fastest possible rate of access, because in the burst mode you will halt the CPU. Okay, you will halt the CPU from accessing the bus, and you can have full access to move your data around. So it's the fastest way of doing it. All right, but of course during that time your CPU cannot make use of the bus. Okay, but it's the fastest way of data transfer. The other way is the cycle steal mode, where you want the CPU to interleave with the DMA. So what will happen is within one cycle, your DMA and your CPU will take turns. Okay, so the DMA and CPU will continuously take turns, where at one point of time is DMA address and DMA data. Then the next half of the cycle will be CPU address and CPU data. Okay, so again, all of this is transparent to us. Okay, if I want to use the DMA, I activate the DMA based on the registers involved. Okay, so the DMA is just like your serial port or your I2C or anything else. All right, so if I want to use the peripheral, I need to go and configure all the registers, say what I need to do, what how much memory I need to move, what is the starting address, what is the ending address, put in all this information and start the process. Okay, once it is done, I'll be able to get some interrupt or get some response to say that the DMA move is complete, and then I can go on. Okay, so in the KL25Z, okay, this is basically what you have. You have 4-channel DMA. Okay, that means you can activate DMA, okay, for 4 different channels. All right, and at the same time you have a DMA mux as well, so you can have multiple devices that want to use the DMA. Okay, so you can have multiple memory blocks or subsystems, and then you can use the DMA mux to sort of decide which of these peripheral blocks will use which channel. Okay, so it is quite a complex system. So you can have multiple devices. So you can have 12 devices, 13 devices, all say they want to use DMA, but you only have 4 channels, correct? So your DMA mux is where you configure and say at this time which device gets to use the DMA. All right, so it is quite a powerful system. It's good, okay, that we have it. All right, and something that you can try, okay, when you are free. All right, but you don't need to use it for the project or anything, because we do not have huge amounts of memory to move around or anything like that. Okay, so but it's good to know. Okay, so if you want to use the board in the future for video processing or audio processing and things like that, okay, you can consider DMA as an option if you have large chunks of data to move around. Okay, so basically that is the end of the module. Okay, so well done. You can give yourself a pat on the back. All right. So with this module, we have, okay, I've tried to make sure that we cover RTOS concepts together with embedded systems, okay, integrated, okay, because, okay, I mean, before I decide to change the scope of this module, I did some research on my own, looking at other universities, okay, that are also very well known in computer engineering programs, and I looked at how they structured their courses, and I felt that most of them did a similar approach. Correct? That means RTOS for embedded or computer engineering is very much a practical based learning approach that is taken. So that is why I changed the approach, okay, to make it sort of in this direction. And I can see that it is good, because in the lab, okay, when you are doing your project and so on, you think a lot, correct, about how to use the OS effectively to do all the things you need to do. All right, and that is where the learning comes. All right, because if you just learn theoretically, you do some software simulation, you will not really appreciate it. Correct, but now when you're dealing it with real hardware in a real system, you can see that how changing certain aspects of your code, or how you use the semaphore or the message queue, everything will impact the way the system behaves. Okay, so that is, I think, a good point of moving in this direction. And I'm happy I've done this. And so far the feedback from most students is they really like this module. So I hope you have also liked this module. So next thing is, of course, marketing for my next semester. Okay, so if you are keen to be a TA, you can let me know. I will send out emails to you all sometime in December as well, just to give you all a reminder. Okay, uh, so for now, what we will do is this. Okay, so in the tutorial questions, okay, so the tutorial question, the last two questions are on the DMA concept as well as the memory address decoding. Okay, so what I will do is we can have a break, and I'll send you all to breakout rooms at the same time to have a discussion on these two questions, all right, on the DMA question as well as this address decoding. When we come back, I will review both these questions with you, and then we will wrap up with some final announcements for the exam as well as the project. Okay, so you can go for your break now, and at the same time, I will send you all to your breakout rooms. Okay. Okay, so welcome back. Okay, so let me just show you something regarding the KL25Z's memory map, so you can relate to it a bit better, and then we'll go through the tutorial questions. Okay, so this is one of the code that we had before on the mutex. So I'm just going to run it. Okay, so this is basically to blink the LEDs. Okay, so let me remove the breakpoint first. Okay, so now the code is running, so the LED is flashing. Okay, so I just want to put a breakpoint and just show you two things. Okay. Okay, so if you look at two things here, basically what I want to show you is, let me see if I can. Okay, I can't really zoom in here. Okay, but if you look here, there's two things. One is the PC and the SP, the program counter and the stack pointer. If you look at the program counter, the value is 1F36. The stack pointer's value is 1FFFF2E0, correct? So definitely we know that when your program has already been flashed onto the board, it has to occupy a memory location that is representing where the flash is stored, and your stack pointer is pointing to a RAM space, correct? So that you can hold or push and pop variables while your program is executing. Okay, so you can relate this back, okay, by opening up your KL25Z's memory map. Okay, so if you open a data sheet, you have your system memory map. So you can see that the first few locations, okay, is up to 7FFFFF, is all your program flash, okay, your program flash. So that corresponds with what we are seeing for the program counter. Okay, 1F36 is within the initial memory range that is for the program flash. And similarly for the stack pointer, you can see that it's 1FFFF2E0, which is corresponding to the SRAM region. Okay, this region over here. Okay, so this is basically the full memory map of your KL25Z. Okay, so if you look back at your registers for your different peripherals and so on, okay, you will be able to see that they are mapped to all these different registers over here. So for example, your GPIO, okay, you can see that they are mapped to this particular address location. So all the registers associated with the GPIO peripheral block are somewhere between this address range and this address range. Okay, so similarly for your other subsystems and so on. Okay, so this is basically what is happening at the back end when you are designing a system. All right, that means from a processor, you are putting together the memory, the flash, the peripheral blocks, everything, and you want to create a memory map for the system. that is where this memory decoding approach will come in, correct, for you to understand how to uh, place all these various components in the memory address space that your controller has or your processor has. Okay, so let me now go through the tutorial questions. Space, I'll come back to it later. Okay, so question 1 and 2, I've asked the TAs to go through with you all in the in your tutorial slot. Okay, question 3 and 4 is what I'll go through with you all. So question 3, basically you are required to develop a program that will move 1 megabyte of data from address C000 to D000. Okay, so you must update the progress of the data transfer every 1 kilobyte of data. Okay, so basically what you have is in your memory map. Okay, you have a memory map and you have 1 megabyte of data starting at address C0000000, and you want to move this 1 megabyte of data over to address, okay, starting at D0000000. Okay, and it's not just one complete move. You also want to make sure that every 1 kilobyte of data transfer, you want to update the LCD panel that you have on the system. Okay, so every 1 kilobyte you update. Okay, so like a progress bar or something, and then at the same time, when you finish, you also want to sort of know that you're completed. Correct. So how do you go about doing this? All right. So obviously there are two ways, correct? And the two ways, the first one is by using your normal loop, correct, plus copy paste. Okay, so what is a normal loop plus copy paste? It is basically, okay, so I can just show you the answer to discuss further. So this is something like that, correct? That means you take you write a loop, all right, and then you take from the source and you copy over to the destination. And if you are having a multiple of 1 kilobyte, then you call a function to update the LCD screen. All right, so this is basically something that we will do, correct, if we do not know of any other option, correct, because this is the easiest way, correct. I just copy from one place, paste to another place, and do it in a loop until I finish the complete data transfer. All right. Of course, this is very inefficient because you are making use of the CPU to just move data chunks around while you could have been doing something else. All right. So a more efficient approach, okay, would be to use the DMA, like what we just saw. The DMA again is not available in all microcontrollers. Okay, if you would use the Arduino Uno, for example, it doesn't have DMA. Okay, so you can't do a DMA transfer there. All right, but Arduino others. Other high-end Arduinos do have DMA. Okay, so you need to look at the controller and to see whether it is DMA, and then you can consider using that. Okay, if you have this kind of requirements. Okay, so for the KL25Z, if you're going to do something like this, the better approach would be to use DMA. Okay, so to use DMA, you need to set up the DMA. Okay, just like your normal UART or serial and SPI bus or anything, you need to make sure you set it up with all the correct configuration, and then you can sort of activate it and it will just start to run. Okay, so how do I set it up? Okay, so there are 4 steps involved. Okay, so the first step is you write the start address and number of words to be transferred in DMA registers. All right, so you need to say which is the address from which you're copying from and moving to. All right, and how much of data you're going to move into. So the DMAC has some registers, okay, that you need to do this too. Okay, so I can show you back the slide here. Okay, so if you remember this slide just now, we looked at it. So you can see that each channel, there are some registers involved: SAR, DAR, DSR, DCR, and so on. So these registers, okay, are the ones that will hold this information on what is the start address, the end address, and so on. Okay, so the details, of course, we need to look back at the data sheet to understand how to program these registers. Okay, but basically the idea is you need to make sure you program this information into the appropriate registers. Okay, so for DMA, we did not go through in the actual implementation specific, so it's just the concept of how to do it. Correct. If you really want to do it, then you need to look into the data sheet and look at all the registers and do and figure out the steps involved. Correct. But in general, you need to make sure you program the registers with this information, the start address and the amount of data to be transferred. Okay. You can set the DMA controller to automatically increment. All right. So you can say that after I move 1 byte, I straight away increment to the next byte. Or if I move by 1 word, I can straight away say I increment by 1 word. Okay. So these are all settings that are configurable in the registers of the DMAC. Okay. You can also configure the DMAC to generate interrupt. Okay. So once you are done, you can say generate interrupt so that you know that you have completed it. All right. And what you can do is you can, instead of putting it as 1 megabyte, you do a DMAC for 1 kilobyte. Okay, why? Because every 1 kilobyte, when you get the interrupt, then I can update the LCD and then I can reset or readjust my register values to point to the next 1 kilobyte. Okay, and do the next transfer and so on. Okay, so you can sort of think of different ways of using the DMAC in this aspect. Okay, but the whole idea is this requires the DMAC to be available, correct? And with the DMAC, you can free up the CPU to do a lot of other things, all right, which will be more useful instead of just moving data around. Okay, so that is basically the idea of how you can use the DMA in your design or in your application. Okay, so now let's look at the next question. Okay, so the next question is on the memory map design. Okay, so in this case, what we have is we have a microprocessor system with this memory map as shown below. Okay, provide the starting and ending address for each of these devices. Okay, so that's the first thing we need to do. Okay, so what I've given you this 3 steps is basically the 3 steps you need to do if you need to design an address decoding circuit. Okay, so the first thing is you want to come up with the first starting and ending address. Okay, so how do you do this? So you need to look at it from the amount of space that you need to access. Now 2K ROM. So 2K is basically 2048 in hexadecimal is how much? Okay, 2K in hexadecimal is 0x800, correct? Okay, so if 0x800 means if I'm starting at 0000, I will end at 07FF. Okay, so the starting for this will be 0000, ending at 07FF. Okay, now the next thing, I have 2 8K RAMs over here. Okay, RAM 1 and RAM 2. Okay, so we say that we know that 8K is 8192 in hexadecimal is hex 2000. Okay, so if the ending address of the 8K RAM 2 is 9FFF, what is the starting address? Okay, so the starting address will be 8000, correct? Correct. So if I'm starting the RAM to 8000, then the RAM 1 is ending at 7FFF, correct? And since that is also 8K, that means it's hex 2000. So if I subtract, I will get the starting address as 6000. So all these are in hexadecimal, correct? And then the last one is the 16K RAM 3. So 16K is 16384, which is 0x4000. So if I end at FFFF, I start at what address? C000, correct? Okay, so that is basically the starting and ending address of each of the different systems or peripherals you have in your memory map. Okay, now what is the next step you must do? you must give the address decoding logic. Okay, so what is the address decoding logic? So the address decoding logic means you need to look back at the entire address bus and figure out for each of these devices which address pins will remain constant and which address pins will change. Okay, because the ones that change are the ones that will go to the address bus of the device. The ones that will remain constant are the ones that will be used for the decoding. Okay, so let me show you how to do it. So the way you can do it is you can first write out the address, let's say A15, A14, A13, A12, A11. Okay, so the minimum I need here is so it's up to, so this 2K memory chip. Okay, so for the 2K memory chip means it is how many bits here? 12 bits, correct? So I need total of 12 bits to address this device here. Okay, so for this, basically what it means is, since I am starting at 0000 and I'm ending at 07FF, okay, you can see that this first zero over here is corresponding to, okay, this first zero over here is corresponding to A15 to A12. Okay, that means the upper bits are all going to be 0. Okay, now what you then need to do is you need to look at the next bit. Okay, so we can see that when I addressing the 2K ROM1, the upper 4 bits A15 to A12 will be 0. Okay, starting also 0, ending also 0. Okay, so all 4 will be 0. Now let's look at the next hex over here, which is 0 to 7. So 0 to 7 means I'm starting from 0000, but I'm ending at 0111, correct? So you can see that the lower 3 bits will change, whereas the upper bit here will remain constant. Okay, so that bit is also over here. It's part of the bit that remains constant throughout the memory access of this 2K ROM chip. Okay, all the other bits, okay, from A10 down to A0, all of them will change, correct? So they will start off, okay, they will start off with 0, 0, and the ending address of this memory chip will be what? The ending address of the memory chip will be 0000, 0, and this will be 1 all the way to 1. Okay, so you can see that the lower 11 bits here, A0 to A11, are the ones that will be changing, whereas the bits over here, A15 to A11, will all remain constant as 0 while I'm accessing this 2K ROM chip. All right, so I can use this as the way to decode my 2K ROM1. Okay, so let's look at the next example. If you're still not sure, let's look at the next example, then you'll see the pattern. All right, so let's look at this device over here, 8K RAM1. Okay, so for 8K RAM1, let me do it over here. So I'm starting at 6000 and I'm ending at 7FFF. Okay, so if I'm starting at 6000, 6 is 0110 and 7 is 0111. So what do you observe? You observe that the upper 3 bits here are constant, all right, whereas this bit onwards is changing. Okay, so as I said before, we look at the ones that are constant to use for the decoding. The ones that are changing are the ones that will go to the memory chip. Okay, that means in this case, I only need to look at A15, A14, A13. Okay, so as far as this memory chip is concerned, the memory will change from, or the address will change from 0, 1, 1. Okay, then it will be 0, 0, 0 all the way up to 0, 1, 1, 1, 1, 1 all the way. So that will be the address decoding for the 8K sorry 8K RAM 1. Okay, so the upper 3 bits A15, A14, A13 are the ones that remain constant during this access, whereas the lower bits are all changing. Okay, the same analysis for the 8K RAM 2. Okay, so for the 8K RAM 2, again the same thing. We start off with 8000 and with 9FFF. Okay, so this is 1000 and this is 1001. So similarly, you see that the upper 3 bits are constant and the lower bit is changing. So as long as the upper 3 bits are 100, so as long as the upper 3 bits are 100, then the lower 3 bits can be anything. Okay, and that will tell us that we are now going to access the 8K RAM 2. Okay, and then the last one is this C000 to FFFF. So let me do it here. So this is 1100 and this is 1111. So you see that the upper 2 bits are constant and the lower 2 bits are changing. So as long as the upper 2 bits are 1 and 1, okay, the upper 2 bits are 1 and 1, then you are going to access the 16K RAM 3. Okay, so the lower bits will change. Okay, but this will signify that we can just use the upper 2 bits 1 1 to be decoding the 8K RAM 3. Okay, so this is the decoding logic. Okay, that means what we are trying to do is we are trying to look at which are the bits that are constant while I'm trying to access this particular chip. All right, so we can see that for 2K RAM1, I need to use upper 5 bits. For 8K RAM1 and 8K RAM2 is the upper 3 bits for different values. And 16K RAM3 is the upper 2 bits. Okay, so once you have this logic, then you can go ahead to design a circuit, okay, to sort of represent this. Okay, so in the question, what you're given is you're given a hint, okay, to use a 3 to 8 decoder with other discrete logic gates. Okay, so let me show you one possible solution. Okay, so you may have other solutions. Okay, doesn't matter as long as they sort of make logical sense, then it is fine. Okay, so as long as you know that your circuit works because when I have this particular address, a particular chip select is activated, then it is fine. Okay, so let me bring it up here. Okay, so this is a one possible solution only. Okay, you can have other solution. So let's look at this. Okay, so this solution is such that I have type 15, 14, 13 over here. All right, so let's look at what happens. So when it's 0, 0, 0, line 0.
Your screen is not sharing.
Oh, okay, okay. Wait, okay, so let me start again. So this is one possible solution using the 3 to 8 decoder. Okay, so what we have is 15, 14, and 13 is connected to lines 2, 1, and 0. So when I have 0, 0, 0 here, line 0 gets activated. So this here you get a 0. Okay. So when A11 is A12 is 0, A11 is also 0. That is the condition for this, correct? For 2K ROM1. Okay, for 2K ROM1. So when all of them are 0, then this will be a 0. Okay, so in this question, I have assumed active low chip select for the ROM1. Okay, so I want it to be a 0 to activate the ROM1. Okay, so if you have taken it to be otherwise, it is fine. Okay, so as long as you stick with an idea of how you want to design the circuit and what is the chip select logic you're looking at, it is fine to design it either way unless the question specifies. All right, in this question is not specified, so I am just going to say that it is active low chip select for the different devices that I'm selecting. So you can see that if there was a situation where any of the bits became 1 or any of the bits became 1, automatically this would have become a 1, which means that the chip select of ROM1 would not have been selected. Okay, so the only possible combination for the chip select ROM1 to be selected is when A15 all the way to A11 are all 0, then this gets selected. Okay, so this is the first chip. So for the next one, basically for RAM1, for chip select of RAM1 and RAM2. So RAM1 is 0, 1, 1, RAM2 is 1, 0, 0. Okay, so when it's 0, 1, 1, line 3 gets activated. So that directly goes to RAM1. And when it is 1, 0, 0, your RAM2 gets activated. So for RAM1 and RAM2, I don't need to do anything extra because I only need the upper 3 address bits to detect, and those upper 3 bits are already going into the selector pins of the decoder. Okay, so I don't need any other additional logic. Okay, for the last one, which is the RAM, 8K RAM, basically I need to make sure the upper 2 bits are 1. Okay, so when upper 2 bits are 1, it is 1 and 1, and the A13 could be 0 or could be 1. Alright, so if it is 1, 1, 0, the line 6 get activated. Okay, when it's 1, 1, 1, the line 7 get activated. So in this case, this decoder is an active low output. That means when you say activate means it becomes a 0. So when either one is 0, the output of this AND gate would be 0. So I will activate the RAM3. Okay, so if you had chosen active high decoder output, then of course your circuitry will be a bit different. If you have decided that the RAM chips or the ROM chips are all active high chip select, again your circuit would have also been different. Okay, so it all depends on what is the active level of the chip selects that you are trying to activate in your memory map. Okay, so that will sort of decide how the whole circuit is designed. All right, so that is basically one way of designing a address decoding circuit. Okay, using decoders plus additional logic gates like this. Okay, to make sure that your address decoding is matching the memory map logic that you have obtained here. Okay, so that is basically the tutorial questions on the DMA and the memory map. Any questions you all have so far on this? Okay, so if question you can still ask me later after we end. Okay, so that wraps up the tutorial discussion. Let me go on to the just one more set of slides on the mini project and and the exam briefing. Okay, so as you know, next semester there is no more zoning involved, which is good news. All right, so let's just hope that things remain good, okay, during the December holidays. Okay, then when we come back on in January, things will be um, a lot better. All right, and the engineering canteen is also going to open in January. All right, so that is also a good news. Okay, so let me brief you on the project and the exam briefing here. Okay, so the mini project competition run, I just realized today is Friday the 13th. Okay, next Friday. So hopefully it's a lucky day for most of you. All right. So all teams to report to the lab as per the allocated timing. Okay, what is the allocated timing? I will send you all by Monday or Tuesday next week. All right. So basically, we will randomize all the groups in your particular lab slot, and then you will be given a timing to come. Okay, and what you need to do is again you have to follow the timing because you know the lab. Okay, we have to follow the 50 packs maximum, so if suddenly everybody crowds in, it will be a big issue for us. All right, so please stick with the timing. I will tell you all how much timing in advance you can come in. All right, so those who want to come in earlier to do some check or whatever, that is fine. All right, but you need to make sure you try to stick to the allocated slots. Okay, so once you come in, what you need to do is you need to report to the TA. The TA will do the assessment of the requirements checklist. Okay, so the requirements checklist is let me bring it up again over here. Okay, so this is the requirements checklist. Okay, the one that asks you to you must basically demonstrate that your robot can do all of this. Okay, and your TA will verify that this checklist is done. All right, and once your checklist is done, okay, you can come over. Okay, so in the next part will be the competition run. Okay, so the competition run means I briefed you on Friday. I'll go through now again. So you have 2 attempts. Okay, and both these attempts must be taken consecutively. That means you take one attempt. All right, you cannot say I go for lunch break, come back again and take. No. Okay, you take already. You can take one more time. Okay, the good part is we will take the best score. So even if you whatever happens doesn't matter, you still try your best for both the runs. Okay, so we will take the best score from both. Okay, so the leaderboard is basically the where you stand amongst everybody, all the other teams. So this I can only release after everybody has completed. All right, so later on in the day or over the weekend I'll do it. All right, but basically you will have the 2 attempts that you can take, and then we will take the best score. The exact scoring rubrics I will release to you all by this Friday. All right, so definitely there will be some penalty involved when you bang the cone or you get stuck on the ramp or something like that. All right, so those penalty marks and how we're going to do the timing, I will tell you all by Friday. Okay, so on Friday, basically once you are done with the competition run, I mean next Friday, that's it. Okay, for the project, actual hardware wise, that's it. Like I said, the robot is yours to keep. Okay, and you can do whatever you want with it. All right. The other things that you need to take note is the other deliverables with the project. All right, so the report, the code, and the video. For the report, please follow the page limit that is specified. Okay, so again, let me go through the document here. So it's only 4 soft copy pages. Okay, that means if you were to print, okay, imagine if you print out double-sided means it's 2 pages, correct? So on a normal soft copy document, it is 4 pages. All right, so maximum 4 pages only. Okay, and you cannot be font size is minimum 10 with minimum 1.5 line spacing. All right, so follow the guidelines strictly. and you have another submission of a 2 to 3 minute video. Again, do not exceed this 3 minutes. Okay, you have to strictly, I mean, for your own personal video, you can do whatever you want, but for submission, it has to be sort of shrunk to 3 minutes. Okay, for the submission. Okay, so for this, okay, okay, so all your OS constructs do not count as global variable. Okay, so your mutex semaphore that you create, all of them are not global variable. Okay, but again, you can create global variable as long as you don't use global variable to just use it to do all your data transfer. Anything that is because your stack size within the task is very limited, so you need to create global variables for your variables. So in that case, it is fine. Okay, but the thing you should not do is create global variable to make it like the default way in which your task will communicate with everything without using message queues or semaphores or anything like that. Okay, so that is the restriction behind global variable. Okay, so for all these other deliverables, the deadline is 22nd November. So I give you an additional 9 days. Okay, so from next Friday, you have another 9 days till Sunday. All right, and to submit all of this. Okay, so since you are given this additional time, there will be no extension after this. Can we use malloc? Yeah, you should be able to use malloc. There should be no issue with that. Okay. Okay, so this is for the mini project. Okay, computation run layout. Okay, let me bring it up over here. Okay, so this is basically okay, so for this Friday, I will ask Uncle Jalil to cordon off this section, the first section. So those of you who are regulars here, I'm sorry. All right, but we need to cordon off and make sure that this space is used for your own testing. All right. All right, so try to use the rest of the space that is available. Okay, so basically you will start at the table right next to the door and outside of Uncle Jalil's office. So that will be a start point there. And then, so this is the first section here. This is basically your first section one over here. Maybe the one just beside the Uncle Jalil's office. All right, and you will place the, so beside the table on the left hand side, will place a ramp, right, approximately 276 cm away. So you go straight, you go up and down the ramp, and then the cone. So the cones are there in the left. Okay, so once you come down the ramp, what you need to do is you need to go around the cone and then go through these two cones, and then over here again go around this cone, go up the ramp, and then over here is where you must do a figure 8. Okay, so figure 8 is either this way or this way, up to you. Okay, so you can either go this way or you can go this way. And once you are done, you can go back to the, so the start and the end point is the same. Okay, so there's a pillar over here, so you just go around the pillar and then go back to the end point. Okay, so the leaderboard will be based on a few things, right? Definitely timing, and the penalty marks involved will be when you, let's say you get stuck on the ramp, okay, you cannot go across, or you fall off the ramp, okay, or you hit the cone. Okay, so these are things are the penalty marks involved, which I will let you all know. Okay, so we will cordon off that section, okay, so that we will set it up nicely for you all to try and make sure that there is ample space and time for everybody to give it a shot. Okay, so that is your maze layout. Okay, so let me come back to the slides here. Okay, now let me go on to the exam. So it will be a luminous exam, e-exam, same as your midterm. 2 hours, closed book. there'll be no reference sheet. Okay, no soft copy, no hard copy. Okay, topics will be topic 9 onwards. Okay, so the main focus will be on the RTOS based concepts. Okay, topics 1 to 8, which is on the hardware side, it will be certain parts of it will just come as concepts only. Okay, so it is not, okay, when I say concepts means, for example, I may just say that, okay, you're creating a thread to do serial communication with another thread, okay, and so on. So those kind of concepts will come in, but you will not be asked to program the serial port or what register is involved in the GPIO setting. No, all those things you already did in the midterm. Correct. So topics 1 to 8 is just a concept. Okay, so you must still know what is serial port, you must still know what is PWM, you must still know what is GPIO. All these things you must know, but there is no hardware related programming or the microcontroller based questions involved. Okay, so those were the midterm focus. So the final will be the RTOS focus. Yeah, you can't refer to data sheet, you can't refer to anything. So whatever is needed, I will provide to you in the exam itself. Okay, so there will be no reference sheet involved. Okay, so the type of questions will be similar to tutorial style. Okay, so again, there's no cheat sheet involved because as long as you know the concepts, the questions, you'll know how to answer. Okay, like I said, it's similar to tutorial style questions. Okay, for tutorial style questions, basically, if you see what are the type of questions that is asked, you are given a code, you're asked to analyze, correct? Or you're given a scenario and you're asked to provide how will you use mutex to do this, or how will you semaphore to do this, and so on. Okay, so there will be some coding involved, but again, it will be very minimal coding because it is about only the concepts. That means how you use the semaphore to achieve this, or how would you have used mutex to do this, or something like that. Okay, so whatever information that is required, okay, if there's information required regarding the microcontroller or the OS or anything, whatever is necessary, I will provide in the question paper itself. Okay, so as long as your tutorial questions you have been doing it, and it's not only been high power, then I think should be okay. All right, if you until now have not been going through the tutorial questions, if you've not done any of the actual coding and things like that, then you need to know how to do it. Okay, so pseudocode or full code, I will explain in the question. All right, by default, it is always the proper code, unless I say pseudocode. Okay, so you need to provide the proper code, okay, if you're asked to provide, unless the question specifically says it is a pseudocode. Okay, again, when we say the proper code, doesn't mean you start from main, create thread new, call OS kernel initialize. No, not until that extent. All right, it will be very specific to that particular thing that we are talking about. That means, like I said, if I give you a scenario, okay, that I want to blink the LED in this sequence, how will I use the semaphore or use event flag to do this particular thing? All right, then you need to provide the code for that. Okay. All right, so that is basically what you need to sort of focus on. That means you need to know how to provide the code for that particular focus. All right, so I will give you exactly what you need to provide. Okay, so next week there are no more tutorial questions, there are no more lectures. That's it. Okay, next week tutorial. If you need to have any consultation with your TAs, I will ask them to open up the slot for you all to be available, for them to be available. All right, but there are no more questions involved. There are no more lectures already. This is the last lecture. Okay. Okay, so for today's lecture, we is only until DMA is covered. Okay, the address decoding is not covered in the exam. Okay, I will send an announcement on this to everybody. Okay, so don't worry. Okay, I will send a detailed announcement on the exam and the midterm by this week as well, so that everybody is aware, those who are not in the lecture as well. Okay, how does the MCU check for interrupts? Okay, so that is basically managed by the NVIC, right? The nested vector interrupt controller basically monitors the pins that can generate interrupts, and it will automatically trigger the controller when it detects the event happening. Okay, wait, let me see. Do I have any more slides? Okay, yeah. So this is the last slide. Okay, so again, I think last week I showed you all the slide on contacting the SOC office if you are, or if you feel that you are not in a proper place to take the exam. Okay, so if you think that your home or your hostel or for some reason is not a good place and you want to take the exam in school, you need to email the SOC office, all right, and make sure that they are aware, and then they can make an arrangement for you, okay, where you can sit and do the exam. Okay. Okay, so again, the screen recording is a compulsory thing, all right, for the uh, all SOC based modules. So please make sure that you have tested it and verified that it can record your screen for the full 2 hours. Okay, midterm, there were a lot of hiccups. Some of you say for 2 hours you only recorded your face because it was using the webcam. Okay, so this kind of things happen. Some of you say you didn't know it stopped recording, but it recorded only for 10 minutes. Okay, so these are things that you should test and verify. All right, and also check that you have enough storage space for the recording. Okay, so I think there's one student who said that he used a Mac and it recorded for up to 6 gig or something. Okay, for the midterm. All right, so you need to do your testing. Okay, just keep your screen recorder on for 2 hours while you're using the computer and check that it can do it properly. Okay, without any issues, and check how much storage space it occupies, and make sure you have enough space for that. All right, and I will send you all the details on where to upload it with, and also how to name it. All right, when you upload it. Okay, again, this is compulsory for all SOC exams. Okay, for midterm, we were a bit okay with some of you who had issues. For the final, definitely there will be a lot more stricter regulation on this. Okay, so please make sure you do your testing and make sure it is working. Okay, and the question announcement page will be similar to midterm. All right, that means there will be 2 pages, one for you all to ask questions or submit questions to me, and then for me to post the replies. All right, so make sure that once I send you all the links, make sure you have access to those pages and you have no issues with them. As before, Luminous, as I said before, try to use the Google Chrome because that seems to be the one of the best so far. Okay, students who have tried using other browsers have reported issues in the past. Okay, that the image doesn't show properly or cannot scroll properly or things like that. Okay, so as much as possible, if you can use Google Chrome, do that. Okay, and everything else is how we did the Luminous quiz. Okay, the exam timing, everything, please check on the official notice from the registrar's office. All right, so they will send out the official announcement or the exam schedule, so please check on that and make sure you come in online at that time. Okay, so I will also be sending out announcements this week on all the exam related matters as well as the project related matters. So that's all I have for y'all, and I will see y'all on Friday in the lab. Okay, thank you. Bye.